Good evening and welcome to the Hollerith Lecture on Innovation and Entrepreneurship. The series is supported by Hollerith's grandson, Richard, a former Blair parent of the 80s. Hollerith worked on the national census of 1880 and thereafter invented a punch card system to automate the grueling process of compiling accurate figures. The punch card mechanical system for processing enormous amounts of information, data, was the impetus for the formation of Tabulating Machine Corporation, or the nascent IBM, as I said yesterday in a school meeting. The use of electricity was the very first application of electricity to information handling. The Millennium issue of London's Economist magazine identified Hollerith's machine as one of the 10 most important science and technology events in 1,000 years. His invention was the beginning of today's huge information processing industry. Tonight we build on that because 3D printing is going to be the focus. We are fortunate to have Mr. Ronn Cort here, Emily's dad. He's the president of Kydex, the thermoplastics, the U.S. division of Sekisui Chemical. Emily said it better. An $11 billion chemical and materials-based company out of Japan. Tonight he'll be talking about the advanced technology of 3D printing, something his team is working towards using in the production of thermoplastic parts to be used in things such as aviation, mass transit, and medical device applications. I give you Mr. Ronn Cort.
Hi. Show of hands, who's played on or played with a 3D printer? Okay, leave your resumes as you leave, okay? I need those future jobs. That's great. That's outstanding. So for a lot of you, a lot of this will be old. That's a pretty good group. I recently did this similar presentation at a university, and there weren't that many hands. So you guys are ahead of the curve. That's great. Keep that up. Save your questions to the end. I'm going to try and keep this kind of light, kind of fun. Store your questions. Hold on to them, and we'll come back. All glimpses into the future require a peek into the past. If you don't know your past, you don't know what your future is. You know what that is? Arrowhead. You know how that was made? You know what kind of manufacturing made that? There's additive manufacturing, which is 3D. What's the opposite of additive manufacturing? Subtractive manufacturing. So somebody a long time ago got the idea to take this rock and start knocking pieces off of it, and they turned it into an arrowhead, turned it into something they could actually start to scrape and scavenge with, and that was a kind of a disruptive technology. It turned us from gatherers into hunters. Huge change. So that subtractive technology is literally millions of years old. Another disruptive technology is 3D printing or additive manufacturing. So this is a typical MakerBot. Most of you guys have probably seen MakerBots around. You can buy them for your home, $4,000 or $5,000 for really good machines. What they do is they take nothing. They take a space. They take a polymer, in this case, and it builds it up. So I'm going to pass this around. This is stuff coming off of, that's all 3D printed part, small 3D printed part. To put things in perspective, how slow 3D printing is, the part that we're passing around, that part takes about 2 days to get made on a MakerBot. When we talk about 3D printing, this is what most people think about. Kind of what we would call tchotchkes at work. Small toys, kind of simple consumer goods, phone case. Kind of play at home, you make 1, 2, maybe 5, but you wouldn't make hundreds of them on a 3D printer. It takes too long. It's easier to go out and buy those the way they're made today, which is typically done through subtractive manufacturing. So we're not going to spend a lot of time talking about things like this, as cool as they are, because you can do that in your dorm room for $4,000 or $5,000. Talking about Herman Hollerith, I promised Dr. Miller that I'd connect it somehow. You guys know what Moore's Law is? You heard it before? Show of hands. Okay, you're living it. It's computers. We're starting to hit the limit on this, but computers, the processing power is doubling every 2 years. So I talked to a lot of the companies that we work in 3D printing, both the equipment manufacturers and the material manufacturers, to get an idea how fast 3D technology is advancing. The size and speed of 3D printers is doubling every 3 years. Okay, think about that. So a lot of the things that our customers buy from us, we're talking about billions of dollars of companies. That technology, the way they make it today, will be replaced in 15 to 20 years. Huge amounts of supply chain, huge amounts of shift in terms of how we make things, how we manufacture things. I'm going to spend a moment, give you an idea of what a large-scale 3D printer looks like. This is a large-scale manufacturing 3D printing. It's kind of state-of-the-art today. Give you an idea of what actually is taking place. This is called an Omega Envoy. This is the state-of-the-art in terms of high-end 3D printers. Sped up, obviously, quite a bit. So what our engineers do, our engineers have to do two things. They've got to develop plastics and polymers and materials that can be used in these printers, because there's a very small portfolio of products that can be used in 3D printers today. And most of them are non-structural, that you wouldn't want to fly on them, you wouldn't want your car made of them. They're not robust enough to do structural components. But it's all starting to change now. So I'm going to skip ahead a little bit. I'm going to move up to about... So here you go, about a day later, here's where you are. So now you're making multiple components on one table. Today, how that's done is each of those individual components will be produced by different companies and then assembled all together by a third company. Now it can all be done by one company in-house without having to go out of house. That's a huge shift. That's a massive part, by the way, in 3D printing. It's a big part. So what I'm going to talk about today is not the Yodas, not the chess pieces, not the phone cases. I'm going to talk about what we're doing today in 3D printing in my company and the companies that we work with. So all of these parts are 3D printed. They would normally be done through subtractive manufacturing. A lot of them would be metal. They'd be taken from a piece of aluminum and then kind of tooled down into an individual component. Now they're all built up using new polymers, and most of these use new polymers. U.S. government and NASA, Boeing, Airbus, they're big drivers of this technology. So that's where a lot of the innovation comes from. So I'm going to share with you some of what these parts are actually used for. So there's that first part. That's actually used for NASA research drones. These are sensor covers. So there's sensors sitting on the bottom of these drones that need to be protected from the elements, and they've also got to be impervious to typically radar. So these are new polymers that actually have to replace existing materials that have to be weatherable, have to be structural, and have to be radar transparent. And these are huge challenges from a material standpoint to get them to actually come through print heads in a 3D printer. This is the Airbus helicopter. That's actual component. That's a 3D printed panel. It's a large panel. That's about a 1 week print. That's actually replacing a metal component for the tail rotor section, reducing weight off that helicopter. That total reduction in weight there, it's about 250 pounds, which is massive reduction in weight on a helicopter. Makes the helicopter lighter, more fuel efficient, actually makes it safer as well. One of my favorites, vertical axis wind turbines. These are all individual, each one of these is an individual 3D printed part that assembled together to make a vertical axis wind turbine. Why this is pretty cool is that instead of buying a normal wind turbine with typical geometry, companies can come into that particular geography. So if it's Kansas or New York City or Florida, there's different measurements in terms of how the wind moves, what the gusts are like, the wind patterns. You can actually engineer specific parts made for that particular wind turbine. So no two wind turbines are alike. Everyone's completely individualized for not just the geography, but the location of where it's going to be mounted. Is it going to be mounted on a roof or down on the ground? That was incomprehensible just 3 years ago, that you could customize a large-scale part like this. Big challenge is the polymers that get used aren't weatherable. So right now, these polymers, when they sit out in the sun, they start to degrade. So they're coated and they're covered. The goal is to make weatherable polymers that can do all these other things as well. That technology does not exist yet. One of my favorites, this is NASA's new, as strange as it sounds, they call it their SUV. They are actually starting to build a vehicle that they know they're going to drop up on Mars at one day to allow people to move around the planet. Well, there's only 2 of these in existence. They're pretty amazing. You can actually, if you go into Houston, there's one in Houston and there's one down in Florida. But throughout that vehicle are 3D printed parts. Now you think to yourself, well, they've got tons of money, they can do anything. Why are they making 3D printed parts? Here's what's really interesting. So you're going to drop 2 of these up on Mars sometime, let's hope, next 20 years. If a component breaks, how do you get a replacement part up there? So how this works is you send a 3D printer up with the vehicle. You send the filament up with the vehicle, no spare parts. Something breaks, you call back and you go, I need the file to make this particular component. Oh, and by the way, I need the file to produce the wrench and the sprockets to assemble it and disassemble it. So you don't ship anything with it. You literally just send the files up, print locally. Now, the real challenge is, well, how do you replace the filament? Here's the best part. Emerging technology allows you to take some of this polymer, and there's machines now where you can take the polymer, grind the polymer up, and turn it into new filament. So as the parts break, you take the parts, you feed them back in the machine granulates them, makes new filament, you can make parts. So the challenge for material technology people is that material can only go through so many cycles. So how do we make these polymers have multiple heat cycles? How do you make them go 10, 15, 20 times and still maintain all their physical properties? Huge challenges being worked on today. A lot of nanotechnology, a lot of nanotube technology doing that, a lot of ceramic technology around that relative to ceramics and polymers. But this is bleeding edge stuff. This is just starting now. As you guys come out of college, you guys come out of university, this is going to be mainstream technology. It's just, literally, you are on the cusp of this massive wave and change relative to materials. I'll show you. This is a kind of a strange video. It's not really a public video, but it's skip ahead a little bit. Here's this thing in action, which I think is pretty impressive because there's 2 of these exist. It does run. So the idea here is that rather than send people out on space tubes and they walk, 150 yards from their station, they can go out for 10, 12, 14-day journeys, self-contained. But then, if something breaks, they've got to be able to repair it right there on the spot. That's where 3D printing comes in. Without 3D printing, this wouldn't be possible. They've got to be able to replace these parts. This was started about 5 years ago. They expect this to be done in about 10. That's the length of this project. 15-year project. Who knows what the Kármán line is? You know what the Kármán line is? We just talked about being on Mars. The Kármán line is the break between inner space and outer space. That's that line where outer space officially starts. So we're going to go a little bit lower. Look kind of familiar? Has anybody not been on a plane? There's somebody. Don't feel bad. Buses are safe. You know what makes this plane unique? And you know what makes this plane a little bit unique, this plane interior unique? Anybody?
Fireproof.
That's part of it. You hardly ever see this. How many rows, how many seats on this side? You don't see too many planes like that of this size, 2 and 3. It's a strange layout. But all of these gray parts today that I've got outlined here in red, those are all thermoplastics. Our company makes this polymer to make these parts. So our materials are used in many markets. The one that we're probably most well known for is commercial aircraft interiors. So our material today is made to produce those components. There's a massive supply chain. So we sell our sheets, we make sheets, we take this polymer, we turn it into sheets, and I'll go through this. And then there's people who turn those sheets into these actual parts. 3D printing is going to take away 4 or 5 industries to be able to make that same part. I'll show you how it works. Today, these parts are made in 8 easy steps. I put quotes around easy because it's not. These are very difficult parts to make. Step 1, we extrude plastic sheets. That's an extruder. We have 14 of these making plastic sheet. 24 hours a day, 7 days a week, these things are cranking out rectangles all day long. That was my dream growing up. People said, what do you want to do when you grow up? I said, I want to make plastic rectangles. That's what our company really does, is we make plastic rectangles. Extruded sheets. What are extruded sheets? What's an extruder? A show of hands, who's ever used or worked with an extruder? Okay, so 3 of you. Every hand should be up. Emily, put your hand up. You've worked with an extruder. Matter of fact, everybody's hand should be up. That's extruder 101. All we do is the exact same thing, just really big. Okay, we're taking polymers, putting polymers into a barrel, pushing it out through this die, and then we're cutting those into rectangles. Those rectangles get bundled up and shipped out. All right, so step 1, we extrude sheets. Step 2, somebody has to design the part. So there's this tray table that comes down. There's an engineer who designs that part. I need the tray table to look like this, have these dimensions, this thickness, needs to fold into the seat back ahead of it. He's designing the plastic part. Once that file's done, what he does, he takes that file, he hands it off to a completely different company, but then has to design a mold or a tool to make that plastic part. That plastic part now has to be molded over something. So this engineer is now actually making the tool over to which to mold that part. Step 3, they've got to purchase aluminum billet. So now somebody's got to cast aluminum, right? Huge amounts of energy, huge amounts of natural resources to make this aluminum block really big, really wide, perfectly made, goes through all this quality check because it's got to be spot on. It's not scrap, it's really expensive, hard to make. Then we take that aluminum billet, and then the first thing that we do with that big, expensive piece of aluminum billet is this. We subject it to the Terminator. We take this perfectly good, beautiful piece of aluminum billet, and we rip the crap out of it. And we turn it into a mold. We turn it into a tool that looks like a tray table, but it's metal. That takes hours. This goes on all day, all over the globe, 24 hours a day, 7 days a week. There's people doing this constantly, ripping metal, big blocks of metal, down into smaller parts, which are just being used to mold something over. All right? So step 6, now that we have this aluminum mold, we've got to turn that plastic sheet, that rigid plastic sheet, we've got to turn it into some sort of like tray table. We've got to turn it into something that you can eat off of. It's got a place to hold your cup, right? In case there's bad weather, you don't want to slide it off and drop it on your lap, or worse yet, the person next to you. Right? So there's a process called thermoforming. It's a different part, but general idea. That's the tool. That's a big piece of aluminum. There's a plastic sheet right there. It's heated up. Pull the vacuum out. The plastic sheet molds around the plastic tool. I mean, the metal tool. So did you get that? Big plastic sheet goes in the oven, gets heated up to about 350 degrees. Again, huge amounts of energy to heat this plastic sheet up. That sheet goes over that aluminum mold, goes on top of it. Pull a vacuum out, take all the air out. The sheet wraps around that aluminum tool. We're still not done because now we've got to use more energy. Again, we're going to rip something apart. Now we're going to go and trim that part out from the bigger piece of plastic. So we've got a big piece of plastic, the part's inside the middle. Now I've got to cut all that other plastic away. Same exact thing. Huge amounts of energy, cutting away just all this plastic. You know what happens to all this trim? Because all this now is scrap. That's the part on the inside. We're just cutting all this away. This is all going to disappear. All that scrap either gets recycled or if the company's not doing the right thing, gets landfilled. That goes on all the time. We take everything back. We're a zero landfill facility. But lots of our competition would just say, you can do whatever you want with that. The people that make those tray tables, they throw it into a bin, they throw it into a big trash compactor, gets picked up by trucks, dropped off at landfill, and it'll be there in 175,000 years because it doesn't break down. It'll be there in a million years, it's not going to break down. So big challenges with that from an environmental standpoint. So then the last step of that process is assemble that plastic part onto the seat. That takes months. That whole process I just showed you takes months. Here's how it gets done in the next 10 years, maybe 5. It's happening really fast, faster than you can imagine. Same parts, 3D printing, 4 steps. 1, that extruder, that's a filament extruder. You saw the sheet extruder earlier, right? Sheet extruder is about 3 times the height of my height. This, I can actually put my hand right about here. So it's about this high. I can fit about 15 of those where I can fit 1 sheet extruder. And all those things do is crank out filament, polymer filament, all day long, 24 hours a day, cranking out filament in colors. So we take that filament. Now we've got a design engineer who's not designing the tool, he's only designing the part now. So that whole design engineer about making the tool, the whole part of making the tool, designing the tool, that's all gone. So that part design, step 3, gets uploaded into a large format 3D printer, you hit print, and it's going to crank out tray table. The challenge today is we can't make enough of them fast enough. There's not enough machines with enough speed to crank out enough tray tables to keep those planes with tray tables. That's just a matter of time. That'll happen every 3 years. These machines are getting twice as big and twice as fast every 3 years. Step 4, same exact thing. Assemble it onto the seat. Now here's the really cool part. Here's the game changer. This is the part where everybody goes, holy cow, this is interesting. This is really interesting. Tray table's broken. If that tray table was broken a little bit more where it wasn't staying up, the FAA says if that tray table can't stay up on its own, we're going to ground that aircraft. It's a safety issue. You don't want that road blocked. Somebody needs to get out. The tray table doesn't stay up or it's broken, big piece of plastic hanging off. That plane cannot fly. That's called an AOG. It's called an aircraft on ground. If we get a phone call in our customer service department that says there's an AOG costs an airline approximately $100,000 a day. When an aircraft is on the ground and can't fly, they lose at least $100,000 a day. So AOG is a big deal. The problem is they might not have that tray table sitting at that particular airport when that plane came down. So now that aircraft's taken out of service, somebody calls up and says, oh, we don't have that part in Newark, but we do have it in LA. And they're going to fly that part at 1 tray table from LA over to Newark, get it on the aircraft. Takes a couple of days. In the meantime, everybody's screaming, everybody's panicked, because you're talking about a lot of money. In the future, here's what it looks like. Flight attendant calls United Ground Services and says, the flight that we're on, just had a tray table break. We're due in about an hour and a half. It's row 31, seat B, tray table's broken. Engineer walks over at the airport, types up that file, loads that file into the 3D printer, immediately starts to print the tray table. That aircraft hits the ground 2.5 hours later, there's a tray table to replace the broken tray table. That kills FedEx, who's flying the tray tables back and forth for United. That destroys all of the supply industry that makes those tray tables. Tons of businesses start to collapse under this model. So, that's why you have to be in 3D printing if you're in manufacturing today, because that's the kinds of shift they're taking on. So that's a huge change, and this is all being done right now. Really interesting study from Boston Consulting Group said that if the airlines in North America were to replace 10% of their broken parts with 3D printed parts, it saves a neighborhood of $2.5 billion a year. So think about the incentive for people to start to move into 3D printing. How am I doing on time? I don't want to get thrown out. We have some challenges. Our industry has a challenge. And this is where you guys come in. Here's where there's gaps. Here's where there's massive gaps. Material sciences, advanced materials and polymer engineers. Material engineers, I will kill for a material engineer. You know how you find material engineers today? You call up somebody who's got one, you find out how much the guy makes, and you offer him 20% more. It's the only way to get materials engineers. They're really talented. They're incredibly gifted people because they're creative. They've got a creative side to them. And they are the future to where we're going. Because 3D printing, the technology itself, pretty easy. It's 30 years old, pretty well vetted. Everyone kind of knows where it's going. We know how to make print heads. We know how to do the mechanics around it. What we're missing are materials. Virginia Tech's got they literally just started a whole program about 3D printing materials. Sold out like boom, like that. They're filled. They're completely filled because that is the future. Polymer engineers, folks who understand how to take molecules and put them together. There's not enough of them. There are not enough. I have 4 open positions in my organization, and they're all 2 of them are filled by PhDs. I've got 4 openings right now. Those openings have been there for almost 9 months. Emily knows, China, Russia, we have to go all over the globe to bring these people in. We don't have enough of them. Macromolecules, you guys hear of macromolecules? Macromolecules, how to take dissimilar materials and bond them together. How do you take materials that are oil and water, how do you bring them together? Chemically, how do you hold them together? How do you find intermediaries that bring these 2 polymers together? Conductive materials. We're starting to print circuits into the actual parts. So you don't have to have a housing for a computer and then put circuit boards onto it. You can literally print the circuit boards into the actual part. The circuit board becomes part of the outside component. How do you print conductive materials? That's being worked on today. Nanotubes, composite nanotubes. I think you guys had a speaker recently on nanotechnology. Nanotubes, super lightweight molecular structures that would replace metal overnight in terms of strength. The problem with nanotubes is they're really hard to hold together, and there's not enough people working on that technology today. That technology is so new. And ceramics. Ceramics are amazing. Ceramics and polymers, they come together. How do you print ceramics? Ceramics now, high temperature applications, super high temperature applications. Talking about rocket applications. There's been a couple re-entry vehicles designed lately that in the news, you guys don't see this, but the outer shells, which used to be ceramic tiles for heat shields, they're becoming plastic heat shields. Plastics are getting to a point where they can withstand those kinds of temperatures. Polymers and ceramics working together to overcome those kinds of temperatures. Here's another one, energy technology, 3D printing. I'm going to show you shortly a video about a new technology in 3D printing that requires laser, oxygen, and UV. Starting to take some of these more classic types of energy and move them into the production of materials. So, materials require energy to be produced. Our traditional energy, carbon-based energy, isn't cutting it. It's not what we need. So there's lots of opportunity here, laser, oxygen, UV, this type of chemistry to turn it into energy. Really interesting stuff taking place there. And design engineering, big shift taking place. Remember I talked about one guy produces the part and the other guy produces the tool? Those are typically two very different engineers. Different way of thinking, different way of kind of approaching problems. The guy who's designing the tray table tends to be a little bit more creative. He's more concerned with the aesthetics of it, more of a, the guy who's designing the packaging. The guy who's designing the tool is more about the nuts and bolts, really technical. Right? There's a gap there because in 3D printing, you've got to be able to do both. You've got to understand the art side of it, but you've also got to embrace that technology side of it. One of the things that we talk about is STEM, right? We talk a lot in our company about STEM, science, technology, engineering, math, right? That's not enough. We want STEAM. I want the art part in there, because without art, there's no STEAM, and without STEAM, without that STEAM, there's no power. We have to tear that STEM into STEAM. If you're just the nuts and bolts, you're going to be great for making tools, but you've got to have that creative side and take that vision and turn that into a three-dimensional part and then know how to actually do the math around that. Those are the most gifted people in 3D printing, often have a more liberal arts background. They've reached out, they've explored that side. Those are the ones that really shine in 3D printing. Those are the ones who are doing some really creative stuff in 3D. So I encourage you to explore that side. If you're more on the traditional engineering minded, reach out, find that creative side, or hook up with somebody who's creative and start to learn how they think. It's a very different thing. When they come together, it's really powerful. All right? Emily got a preview of this last night, right, Em? Is that okay? To call you out loud like that? Shout out, friends. 2014. This was state-of-the-art in 3D printed cars. You guys ever see this? Have you ever seen this? 3D printed car in 2014. That was state-of-the-art. Just a year ago, exactly a year ago. That was it. I just came back from a 3D conference about the future of technology. Spent the whole week there. 2014, this is what rolled out last week. That's a 3D printed car. I'm excited because that's all our power. That's how quickly that technology is changing. I wouldn't want to drive in that, to be honest with you. I got to be honest, I wouldn't be in an accident. Let's put it that way. I wouldn't want to have an accident in that car. But look at that change in 1 year. That's how quickly this technology is moving on. This is a great little video. Because it's not all being done here, it's being done everywhere. China, go big.
It's like an average home. Get a little closer and you'll see the multiple layers that created this 3D printed villa. It's part of
It's
a
a 3D
display in
printed house.
Eastern China showing the latest feat in innovative construction and includes this 5-story apartment building thought to be the tallest 3D printed building in the world.
We transfer the design of the house we want to the printing machine, and then the ink is sprayed layer by layer. This 1,100 square meter building, for instance, which has 3 floors, it took us 1 day per floor.
Record speed that's made possible by a giant 3D printing machine, measuring 105 feet long and 21 feet tall. Instead of ink, the printer squirts out a paste made from recycled waste materials. With larger homes like this villa costing about $161,000 to produce, many are saying it could be a game changer for the construction industry, particularly in countries like China that are facing rapid urbanization.
I think this technology is going to change the way buildings are built. It's going to be attractive to all income brackets.
You'll find this interesting. So why is this back in the U.S. over in China talking about 3D printing? 90% of the 3D printing technology is right here. So this is in the U.S. It's one of our big kind of intellectual capital that we really have got a great head start.
That they would really like.
So we're starting to move it and export
It
it.
already has 10 orders for the villa and 20,000.
Now this is for me, this is the moment where I was like, okay, I get it. This is really interesting. This is only about a month old. This is the first commercialization of this technology. This is called CLIP, Continuous Liquid Interface Production. Right? So normally 3D printing builds up layer by layer. Right? What this technology does is, that's a liquid resin. On the bottom of this tray, the best way I can describe it, it's a projection screen projecting UV. Then there's this permeable oxygen membrane, a couple microns thick at the very bottom of this little pool that keeps the resin in a liquid state. The UV comes up from underneath. So imagine this, the UV screen is got a picture. It flashes a picture, the UV hardens the resin, and then that rises up, hardens it again, then another picture, snap, snap, snap. It's snapping pictures all the time as this part comes out. And I'll show you what this looks like. This increases the speed of 3D printing tenfold. It's brand new though, it's brand new technology. So it's just a pool of liquid, that's all it is. Underneath the UVs, pop, 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 building parts, curing the resin as it comes up. Wow. Amazing? Wow. A little Terminator, right? A little. There you go. And in 20 years, there'll be large scale going on all over the place, all over the globe, making something from nothing. Now, you know where I want to be? I want to be the company making that resin. Everybody talk about materials engineers? There's not enough people working on that. Plenty of people working on this. Not enough people working on that. All right? So, I wanted to share with you, what do engineers do when they're working late at night? You guys kind of go into late at night sometimes, right? And you get kind of punchy, tired. Here's what a bunch of 3D printing guys do late at night when they get a little bit punchy, a little bit tired. I thought you would enjoy this. This is what my kinds of guys do late at night. The science is a little bit trial and error, right? Fail. Now this would be worth having in your room, right? Fail. 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 Mistakes are great. We love mistakes. The more mistakes you make, the more you learn. Enthusiastically fail. Everybody talked about materials? Materials matter. It's not the right material, is it? Technology is great. And eventually, you run out of material. A lot of material. There you go. Thank you very much. Questions? In the back?
A few weeks ago, I saw a video of a guy who just rented a 3D printer, downloaded a file off the internet, and could build every single component needed to assemble a gun.
Yes.
Some people would say that this is what the founding fathers had in mind when they the Second Amendment, but most would say that it's an irresponsible use of the technology. Is there a way to regulate people from making weapons in their house without government knowing?
If somebody wants to do harm, they're going to find a way to do harm. People were building guns years ago. It's the exact same way. I mean, just because they would go out and they would find stock and they would build stock and they would assemble guns. So I don't believe that technology should be regulated. I think that needs to be the technology needs to be open. If people are going to do wrong, they're going to do wrong. I mean, that's just the way it is for me. It's a shame, but just what happens. I'm going to work my way from the back. Hans.
I was just wondering, are there unforeseen environmental implications in sort of the increased plastic usage and plasticization of everything?
Unforeseen? Probably. I don't think we know, because whenever you push something down, something else pops up. There's a lot of bioplastics being used now. People talk about bioplastics. I'm really against that in a big way because it's just the energy required to make crops, to make bioplastics frightens me. I think, what people don't realize about plastics, plastics are actually a byproduct. Plastics are a very small part of all that oil that we pull out of the ground. A very small percentage of it actually goes to plastics. So what drove the plastics industry originally was that when we were taking oil out of the ground, refining it to turn it into fuel for our cars and for our homes and for energy, there were byproducts from that. Things like hexane, benzene, right? There were things that were coming off of there that we didn't know what to do with. You know what we used to do back in the 30s, 40s? We used to burn them. So hexane, benzene, acrylbutyl styrenes, all that stuff is scrap from that process. We've been able to take that scrap and turn it into polymers. So in some respects, you almost want more polymers to use that stock up, to use that off material. I think the biggest change is the carbon footprint of not moving materials around the globe is probably the biggest advantage, and that'll probably offset any kind of negative that we don't know yet. I mean, there's always going to be a negative side of this technology, but just moving materials around the globe, that stops. Right? You're really just moving filament. There's a couple of kids at MIT this was like 2 months ago. They figured out how to take empty water bottles and turn them into filament. So they're taking empty water bottles, PET water bottles, throwing it into a grinder. It's grinding up the PET water bottles, turning them into molten state, and then they're extruding that into filament, which they figured out how to use on 3D printer. So 3D printing could be, and that's what they were doing in China on that building. It could be 3D printing could be to use up all this environmental waste we have, all the plastic that doesn't have homes today. We could start to use that into 3D printing. So it might solve a lot of landfill issues that we have. We might be going back in 200 years, going to our landfills to get that raw material, which is discarded plastic, back into the stream. Yes?
Can you talk a little bit about the accuracy that you can achieve with the 3D printing?
Oh, it's huge. Okay, yeah. Here's the big game changers in 3D printing. Hip replacement joints, right? So you're going to replace a joint. Today what happens is they open you up, they get a general measurement of what that socket, the size of that socket is, and then they find the best off-the-shelf fit for your hip. In the future, what they'll be able to do is they'll be able to image your hip and build that joint exactly to your hip. That's how accurate it is. So you can replace it like for like. That's literally around the corner next couple of years. Dental implants. They can start to do dental implants that exactly mimic your original jaw structure. So they will be rebuilding people from a structural standpoint because you can get that precise. Other questions? Yes.
In the 3D printing version of motor saw, you said the size increases pretty rapidly.
Right.
What limitations are there on that now that will keep it from making it as big as you want?
Speed. Speed is the problem. Speed. You want to scale up in size. Everyone wants to go bigger, but the speed of the print heads isn't there yet, and that all comes down to materials because materials have what's called a melt flow, and they've got to be a certain temperature So if you are heating them too quickly, they turn to liquid. If you're heating them too slowly, they cool. So it's the materials is the limitation, not the speed of the printers. That's not the problem. It's the materials that are flowing through them. That's where all the energy needs to be. Yes. Sorry. Back row. Purple shirt. You. Yes. Sorry. Richard. Yes.
With the thing that pulled the Eiffel Tower under the liquid,
Clip. Yeah.
is that type of speed accessible now? And with that type of thing, do you just need to go bigger? Like,
Just needs to scale up. Yeah. That speed. That's record breaking. That's improving the speed of 3D printing magnitude of 100.
is that going to be on the market soon for like companies to have that? Or is that
Jerry, who runs Carbon 3D, is hoping so because he's going to cash out big. Yes, that you'll start to see that technology. There's a ton of venture capital rolling into that company at the moment, and they have a very good intellectual property protection around it. So what they'll do is they'll license that out over the next 4 or 5 years. You'll see that. That'll be wide scale, probably 4 to 5 years. You'll see that. You wouldn't be able to do that in your home. That's absolutely manufacturing, kind of leading edge. That'll be all over NASA, Boeing, McDonnell Douglas. Those are the ones that are using it first. So, yes.
You've consistently talked about the 3D printing industry kind of killing off other industries, whether it's supply, like you talked about FedEx and the airports, or production, like you talked about with different companies producing different parts. Do you think your view of the future of 3D printing falls a little bit short when approaching things like killing off other industries and perhaps becoming a major monopoly?
No, because whatever is a disruptive technology, there's another technology that moves that one out. So what will happen is those other companies will reinvent. Our company was not in 3D printing 3 years ago. Wasn't even part of our portfolio. We didn't see it. We said, oh, no, we'll be fine. We're fine. We're going to be 25, 30 years making like this. But the rate of change has happened so fast, we as a company have decided to shift. Right?
So how does your company and companies like your company hold on to like information and files about, like, say the airplane tray table? How do you hold on to files like that without letting it grow rampant and kind of everyone holding everything?
Well, that's a tough one. Intellectual property protection, like holding on to our technology. Typically what we do is it's kind of strange for our company, but we're like a technology incubator. We do lots of stuff early. We kind of get like that early adopter curve, and as soon as it starts to become mainstream, we often back out of it. Right? We kind of pull out of it. We always try and grab that early side. So people are always going to take that on. The key is to know when to let it go. So really, really adept companies. The best way to put this is that the mantra that we have is that big companies don't beat small companies. Fast companies beat slow companies. So it's not the size of the company; it's the speed of the company. So what will happen is when I talk about industries going away, they'll shift. They'll find other things to do. They'll reinvent themselves. Right? IBM doesn't make computers. If you'd walk to somebody in 1985 and said IBM's not going to make computers, they'd go, "You're crazy. They're always going to make computers. They invented it. They don't make computers." Right? So what happens is companies will shift. They'll reinvent themselves. That's what disruptive technology does. It makes us stronger, makes us better. Things shift. Someone loses, someone gains. Some people make the shift, some people don't. Right? Yes.
As far as the actual materials that you guys are using, you're talking about using it for space exploration, or I'm assuming it's going to go into other extreme conditions. Do you know the effects of is it tested at all for how materials are going to behave in, say, microgravity or zero gravity,
Yes.
or extreme heat, or even just when it's around for a really long time?
We don't do that. That's what our clients do. So our clients would give us a list of requirements that says we need a polymer that kind of does all these things, has these physical properties, doesn't outgas, doesn't leach, doesn't do these things. It's usually these massive lists of requirements. And then what our engineers do is they start to develop different technologies. They'll take different materials and try and graft them together to invent something that meets all those criteria. Usually what happens is we go back and say, of your list of 130 things, we can give you 104. Right? That's what often what happens is kind of this exercise in compromise. So we've got to start to figure out what really matters, what they have to have, what they want to have. But that testing, they do that testing typically. And we don't always know about that. The stuff that NASA does, we've developed a material specifically for NASA that we have no idea. I have no idea what they're going to do with it. When we can't figure out what it's even for. We have no line of sight to what that would be used for. but they do that higher end testing. Oak Ridge Labs, U.S. Oak Ridge Lab is a massive materials lab. They do a lot of that work. Other questions? Yes.
It sounds like you said it yourself that that 3D printing is moving extremely fast. Have you guys foreseen like any challenges or limitations or restrictions placed on you guys on like your advancement in 3D printing?
Yeah, like what's holding us back from going faster? Or yeah, is that your question?
Yes.
Yeah. What's holding us back from moving quicker is people. We can't find people who have the skills to help us develop this technology. There's a really interesting dynamic that takes place. We've got a group of PhDs that are great, phenomenal when you put them in a room by themselves, say figure it out. But what has to happen in today's environment is collaboration. They have to be able to sit down with other people outside of that laboratory environment and start to have real conversations and real discussions about how to create things that don't exist. That requires a skill set that a lot of people that we bring in don't necessarily have. So one of our challenges is how do you engage somebody? If we're sitting down with one of our customers and clients, how does our scientists or how do our lab folks how do they communicate in a way to get accurate information that they can then turn into something that's valuable? That's a missing skill set that we see. We get these resumes across our desk all the time, and you read the resume and you say the guy's fantastic or the girl's fantastic, and then they walk in and you realize that they're fantastic working on their own. But everything we do is in a team. Customers, clients, industries, it's collaborative work. So there's got to be that connection. Our challenge is finding those people. And that's not just us, that's across the industry. Finding those people, man, it's really difficult. Yes?
Kind of going off that jobs question, you said that the big major or focus for a lot of the college students you're trying to go after is materials engineering. Are there any other specified majors that you do think are important or that your company specifically or other companies in this industry would need? Or is it mainly materials?
No, it's material for us, my company, it's materials. It's really chemistry, for sure. Absolutely chemistry, for sure. Engineering, but I want to put quotes around engineering. It's creative engineering. Not being able to, not to be an AutoCAD jockey, not to know how to use SolidWorks. There's tons of people who know how to do that. It's how to listen to somebody and say, I want something that does this, and then have a dialogue with them that you actually help them almost see their vision differently or better. That's a really unique skill set that a few of our engineers have, and those guys are, I have to put golden handcuffs on them because people try and take them from me all the time. So there's this combination of being a really good engineer, but also being able to move out into a business environment and have those discussions, not just about the technology, but what that technology could mean. So it's engineering for sure, though, for sure. Anything else? Great. Yes, no? Sorry.
Who makes the 3D printers?
Stratasys. There's about 10 companies that do really well. The small companies, MakerBot. There's lots of smaller ones. The really good stuff is Omega and Stratasys. But right now they're all U.S.
And can they be made by 3D printers?
One day. There's actually, I have a joke. I didn't put that slide up there, but there is a guy. I've got a slide where a guy's printing his 3D printer. So eventually, yes, you do 3D printer breaks, but yeah, you could. All right, thanks very much.